Hey there, in this video we're giving an introduction to recursion in C++ programming, and this covers sections 19.1 to 19.3 in the Gaddis textbook. So recursion, an incredibly powerful technique, an incredibly fundamental technique in computing, and what you're going to see here is it provides an alternative way to repetitions. So instead of using loop constructs, you can do this instead, and what you're going to find is it's going to be a lot more elegant in some ways and a lot shorter to create in the code, actually. The computer scientist Alan Perlis wrote in his book Epigrams in Programming, he wrote, "Recursion is the root of computation since it trades description for time," which is a really interesting observation. And if you think back to the very first week of our starter C++ sequence, we said all the time our top philosophical principle is going to be don't repeat yourself. We want our code to be short and readable and easy to understand for other programmers. And I think that's what Alan Perlis was talking about, is that the functions we write here are going to wind up being remarkably short, like amazingly short. In some circumstances, the program might actually run a little bit slower, but if we have to make that trade-off, a lot of the time we would prefer to have the code be short and readable and easy to see there's no bugs in it. For a lot of reasons. So let's get into this and see if you agree with Perlis's idea there. Okay, so first of all, here's the philosophy of recursion. So recursion provides an alternative way of creating repetitions without using any iterative loops. You're not going to see any for loops here, no while loops, no do while loops. You can get repetitions done with a completely different technique here that we call recursion. Now, it resembles to a large degree the principle of mathematical induction, if you know what that is, which is a technique for proving that a particular statement is true for all of the natural numbers. A little bit of a distinction there is that while mathematical induction goes upward, starting at 0 and proving increasing numbers up to infinity, computational recursion has to go downward from some finite number, probably down to 0. Of course, our real-world computational devices are finite. Their algorithms have to get done in a finite number of steps. So our recursion has to be a finite number of steps from some number down to 0. Now, if mathematical induction is new to you, I mean, hopefully you've seen that in a prior math course, but if it's new to you, you'll be talking more about that in your discrete mathematics course, which is essential to any CS program. Where I teach at CUNY Kingsborough, we call that our discrete structures course, which is CS 3500. But that is the course, that's really a math course that gives you all the mathematics you need to be a computing professional. And again, there's a whole chapter there on mathematical induction and computational recursion, which are really just two sides of the same coin. Okay, now what you're going to see here is that how recursion actually works, how the magic works in C++ is that the call stack winds up getting used to save intermediate values. We've talked about that before when we were talking about stacks. Remember, every time you call a function, it stores some information in what's called a stack frame on the call stack. So you get a package of data with all the parameters, right, the local variables, and the address of where you came from gets stored on the call stack so you know how to get back. And what magically happens is those parameter values that are getting saved, you're basically getting free storage as a result. I'll point out that some languages rely solely on recursion for repetitions. They don't have any looping control structures at all. For example, the programming languages Haskell and Scheme and Erlang. The designer said, look, I don't need a for loop or a while or a do while loop. I can just depend on recursion, so why add them to the language? And that's the don't repeat yourself principle taken to a really extreme degree. Is that I can do repetitions with just recursion, so why add anything else to my language? Obviously, we're not going to do that in C++. You need to know about for loops and while loops in C++ or C or Java, but you do have this recursion idea as an alternative. All right, so let's define recursion for computer scientists here. So recursion for us is going to be when a function calls itself. I don't know if you ever thought about a function calling itself, but it totally does work in C++. Some other languages actually doesn't work for, but C, C++, Java, this actually does work. You're in a function, you can actually call that function again from itself. More generally, recursion would be when anything refers back to itself in a circular fashion. So here's a really naive, dumb example, frankly, okay? Here is a function called func1. Doesn't have a return type, doesn't have any parameters to it. All it does is just prints hello to the console. And you see on line 14, there's a function call to itself. There's a function called tofunc1 that's going to send you back into this function again. So that you can compile this, right? This will work. You can run this program in C++. Let's see what happens when you do that. Okay, so here's the call stack. Now, of course, the program starts in the main function. I'm not showing it to you on screen right now. Let's say that line 19 calls func1 initially. So you get the stack frame here. It says, hey, I used to be in the main function on line 19. When you're done with this, you'll come back to me, whenever that happens. So you're in func1, line 13 happens, and you print hello to the screen. All right, and you get to line 14, and you call func1. Okay, fine. So you get a new stack frame, right? That's going to get recorded as that you just a second ago you were in func1 at line 14, and now you're being sent into func1. So line 13 happens, and it prints hello, and it hits line 14, and it calls func1. Okay, well, there's a new stack frame. All right, recording that. Whenever you get done with this, you'll come back there. So you just started up in func1 because of that call. Line 13 happens, and it prints hello, and it calls func1. Okay, you get another stack frame. And you can see what the problem is, why I'm calling this a naive example. It's going to happen over and over and over again, and none of these function calls ever stop, right? This actually winds up causing an infinite loop and ultimately a stack overflow. The call stack it's static, it's a finite size. So if this keeps going like this, at some point, you're going to overwrite that buffer. You're going to run into other parts of memory. You're going to buffer overflow. You're smashing over other memory, and I'm sure something is going to crash. So that's what we call a stack overflow when that happens. And obviously, you don't really want your functions doing that. You don't want your program crashing like that. There's a famous website called Stack Overflow that's a Q&A site for programmers, and the name is kind of an inside joke based on this. As I tried to store so much stuff in my memory that I blew my stack, I ran out of memory, and now I need help to recover from that situation. So that's where that name comes from. Okay, so anyway, this will compile. You can actually try this out. It doesn't really help you because you just get an infinite number of hellos on the screen until the program crashes. Let's see what we can do to fix that. Right, we need to find some way to stop the recursion. So recursion can be made useful if we identify two things about a task. Number one, you need a base case that has a very simple answer. Some version of the problem with a small number that's so simple you can immediately identify what the final answer is. And item two, there's going to be a recursive case where you have a fairly complicated version of the problem and you can do a little bit of work and then solve the problem with one step simpler, right? Makes the problem simpler by one step. And if you do know, so this is really the core, this is really the essential idea to how recursion works when you're designing it. I would recommend, if anything in this lecture, you study this, get this on an index card, get this in some paper notes and study this, because these are the two things you need when you're designing a recursive function. If you do know about mathematical induction, this is very similar to the two things you need there. A proof by mathematical induction has two steps. One is called the base case, and one is called the inductive case, right? It works very, very similar. So the more you know about one, the more you'll know about the other. So when you write the function C++, you're going to get a conditional for the two cases. You're probably going to get an if-else statement, right? That's a conditional. So if you're in the base case, here's the answer. Else, here's the recursive case where you do a little bit of work and then call the same function back with a smaller number. And that'll do some work and call the function back with a smaller number. And the recursive problem will reduce on each call until the base case is reached, and that's what's going to stop the recursion. All right, so that slide right there is probably the most important thing to make sure you digest and understand. But let's see some examples. Okay, so here's a very simple example. This is the countdown function. The idea here is we're going to do a countdown like for a rocket launch. 5, 4, 3, 2, 1, blast off is what's going to happen. And you can see you have this incoming parameter we're calling num. That's what's going to get smaller on each function call to control the recursion. You have the base case on line 13, 14, right? This if statement. If num is 0, that's the smallest thing you're ever going to see here. You know what to print out. You print out the blast off, and the function is over. Okay. Now, the recursive case is the else block down here in line 17, 18. In any other case, you're going to print out that number, right, with ellipses, ... And then here on line 18 is the recursive function call to this same function, countdown, with one number less. That's what recursive functions usually look like, calling themselves with one number less. So you'll call with a smaller number and a smaller number and a small number until at some point it's 0, and then the function actually starts terminating. Let's kind of walk through this. So here's my call stack in this case. Here's the console where stuff is going to get printed. Again, there's a main function. I'm not showing that to you here. Let's say that line 24 calls countdown with the number 3. Okay, so that has to get stored on the call stack. We just called countdown with a number 3. Now to begin with, you get it on line 13 to begin with, and the num is 3, remember. So it checks in on line 13 is num 0, well that's false. So you're going to jump into the else block on line 17, and line 17 prints out, let's see, 3 ... Okay, and then get to line 18, here's the first recursive function call. Now you're going to call countdown with the number 2, of course. So there's your stack frame recording that. You just jumped into countdown with the number 2. Is num 0? Well, no, that's false. So you get down to line 17, you're going to print out 2 ... And now you're on line 18, and you're about to call, right, you printed out 2 ... And now you're about to call countdown with the number 1. Okay, so you get a stack frame recording that, right? Right before we were sent here from line 18, so when this function ends, we better go back there. But we just entered countdown with num 1, so line 13 is false. You get in the else block. Line 17 prints out 1 ... okay? And you call countdown with the number 0. So there's the stack frame for that. Getting in here with the number 0. Now stuff starts working differently. So if num is equal to 0, this is actually true. So it sends you to line 14 and it prints off blast off. Now you skip the else block, of course, right, when you do the if statement. So you're not doing another recursive function call because that's embedded in the else block. Now the countdown function is wrapping up and returning for the first time. What happens then? Well, when you get out of a function, the call stack pops, and then you look here to see where to go back to, and it's saying, hey, you better go back to line 18, back when num was 1. And that's what the call stack is for. Okay, so I'm back on this line 18. Now we're done with that function call. So this function starts wrapping up. There's nothing after that. You come out of this function and the call stack pops, and you get sent back to line 18, back when num was 2. Right, you're done with line 18. So you come out of this function, the call stack pops, and you're back on line 18, back when num was 3. Right? And the function wraps up, it pops again. That sends you back to the main function on line 24 where you came from. And obviously that function returns back to Windows and your program is over. You didn't have an infinite loop. You didn't have a stack overflow and crash your program. This actually did do the correct job. But you do need these two parts. You need the base case, right? In this case, when number was 0, what to do then? And the recursive case, that's the else part, that does a little bit of work, like in this case, just print out the number and some dots, and then calls the function with a smaller number. In this case, just one thing less. And that's generally the flavor of what a properly functioning recursive program looks like. Okay, so think about that. So a couple additional concepts when you're talking recursion, so you have a conversation about it with somebody else later on. You know, recursion is going to be a big part of your future courses. I would expect this to be a big part of an assembly language course. I would expect this to be a big part of a data structures course later on. So this will probably be, you know, we're spending a fairly small amount of time here at the end of our course, but, you know, be prepared to see this in future courses and think about it in greater depth. So sometimes you might talk about direct recursion when a function calls itself, like that example, countdown called itself directly, so direct recursion. But at other times you might have a chain of functions, and in that case you'd call that indirect recursion when function A calls B and B calls A, and A calls B again and B calls A again. Now again, you have to have some sense that the problem or the number is getting smaller on each call, and in those cases it's much easier to have a bug and have an accidental infinite loop and a buffer overflow or something like that. I've written programs that use indirect recursion. You got to be careful about it, but it works. Yep. Now, you can also talk about the recursion depth, which is how many times a function calls itself. That example we just looked at has a depth of 3. Now, if you go back to that prior slide, you may notice that the countdown function was actually called 4 times, but it wasn't recursive until the first time that countdown called itself. Or I guess you could say the first time you get in any function, you're at a recursive depth of 0 the first time. And then when it calls itself, now you're at 1. And to me, I feel that that feels like, you know, the right way to be counting as a computer scientist. So I feel like that makes sense. And it's something you want to kind of keep track of as a designer, because obviously the greater the depth, the more time it's taking, the more stuff is being saved on the call stack, and you need to be careful about that. So occasionally we put like a hard limit on our recursive function, say definitely don't go past a recursive depth of 10 or something like that. You're probably not going to see examples of that in this video, but I've had to deal with that in some programs. Okay, let's look at a couple more examples and think about how you design recursive functions. So here we're going to see a classic example of a recursive factorial function. So we're assuming that you know the mathematics of factorial, right? There's the exclamation mark, you usually use that. And in a math class, you'd probably say that a factorial of some integer n, some non-negative integer n, is that number times one thing less, times one thing less, times one thing less, all the way down to 3 times 2 times 1. For example, 5 factorial is 5 times 4 times 3 times 2 times 1, which works out to be 120. Great. Okay, so everybody already knows that. So how are you going to design a recursive function that doesn't use a for loop, doesn't use a while loop or anything like that, but just relies on the function calling itself with a slightly smaller number? Okay, so you might think about an example there, right? Where is a smaller version of a factorial calculation in front of me in this example? So I'll say that you know, you need these two cases. You need the base case, the recursive case. I usually try to design the recursive case first, because that's the hard part. Once you get the recursive case designed and in your mind, you really have the essence of the problem, and then you can work on the base case later. It's probably so easy you almost don't have to think about it. So where's the recursive case here? All right, so realize this, you know, 5 factorial is really just 5 times 4 factorial. It's got, that calculation has got 4 factorial embedded in it, right? And likewise, 4 factorial is really just 4 times 3 times 2 times 1, and that's 3 factorial. So if you've worked with, you know, big factorial calculations in a math class, frequently you wind up writing them like that. You write out the first couple terms, and then all the rest of it, you just say times, you know, all the rest of the stuff factorial for short. So there's our recursive design right there. If I want 5 factorial, I can just do 5 times the factorial job with one number less. And that always works. That's the trick here. So here's my recursive case, is if I want n factorial, I can always just do n, a little bit of work, times the factorial function with one number less. All right, think about that. Now the base case is very easy, is that again, the mathematical definition of factorial is that if you want 0 factorial, the result is just 1. Right, very similar to any number to the 0 power is 1. That's called the zero product property. I have a math process with no steps, the result ought to be 1, and you can kind of think about that. But the real key here is this recursive case, and that's going to force you to compute a factorial of 1 less, and 1 less, and 1 less, and at some point, if you need to compute 0 factorial, now you know the answer, it's just 1. So, you know, feel free, you know, you're dealing with recursive functions probably for the first time. This may feel a little slippery the first time you think about this, so feel free to pause the video and kind of meditate on whether this fundamentally makes sense about whether these two statements are true. Is n factorial always equal to n times n minus 1 factorial? And when you're ready, restart the video, and we're going to see on the next slide is we're going to write literally exactly that in C++. Okay, so here is the factorial function in program 19.3 in the book. And just like we said, it's a function called factorial. It returns an integer for the answer. It takes one integer as the parameter, like maybe the 5. And here's our base case and recursive case. It's incredibly short. Right? Recursive functions usually look incredibly short like this, and they're pretty much just literally exactly what you'd put in a math class. So here's the base case on line 3132. It says if n is equal to 0, return 1. Yeah, that's the correct factorial for 0 factorial. In any other case, you compute n times the factorial of one number less. And that'll be the answer then. That's it. Right? It almost, like probably the first time you see this, almost looks magical that this does anything at all, but this absolutely does successfully compute any factorial you want. All right, now a couple side notes, right? I would expect to see this example again in your assembly language course or your computer architecture course. It's a very good example in assembly language. Now, you have a whole lot more details that you need to handle in assembly language, but I bet you're going to see that in our program at CUNY Kingsborough. We use the Patterson computer architecture book, and they definitely have that as an example in chapter 2, I would say. So, when you're in the assembly language class and you're handling all these other details, maybe come back and review this, right? The basic idea of the recursive factorial function is very, very simple. So maybe come back and review what the overall idea is, and that might serve as a guide to, the other details that you have to handle at the low-level assembly language situation in that case. At our school, that's the CS 1400 course, which is our assembly language course. So be on the lookout for that. Really good example. So let's test this recursive factorial program in the Gaddis book and kind of think about how this is working. So this is program 19.3 in the Gaddis lecture code. So this has a main function that does your normal user input job. It gets a number from the user, and then it winds up calling this factorial function that we were just looking at. So that's really the interesting thing. Let's look at this. This is exactly what we were talking about there. So let's compile this and run it a couple times. Obviously it compiles. I'll run it a couple times with some numbers and confirm that it works. So first time here, enter an integer value. I'll display its factorial. How about 3? Okay, so the factorial of 3 is 6. Obviously we needed 3 times 2 times 1, and that's totally 6. So that works. And let's try the 5 that we were looking at previously. Okay, the factorial of 5 is 120. Yeah, that's totally what we saw in the lecture slide there. Try something a little bit bigger. Only works on integers, obviously. The factorial function is only mathematically defined for integers. How about 8? So the factorial of 8 is 40,320. Totally correct. Feel free to double check that on a calculator. Right? 1 times 2, 3, 4, 5, 6, 7, 8. That actually is that number. So this actually works. But let's inspect a little bit more closely about how it's actually working. And this is not something you normally have to think about, but just for once, right, in preparation to your assembly language programming course or something like that, let's actually inspect what's happening when you call the factorial function. I'm going to run this in a debugger, specifically with the number 5. Okay, so I entered that 5 example, and let's actually step through this. So what I'm going to do here, get as much space as I can here, is I'm going to open up View CPU Window. Pretty sure we've seen that at least once before in the course. So View CPU Window. Seen this before here. And remember, here in the top left, you have the disassembly, right? That's the assembly code. Again, going to leave all those details for your assembly language, your computer architecture course. Over here on the right, you have the registers, right? The actual contents that's on the CPU. Not very many registers. That's all the integer storage locations visible right there. You got hex, you got decimal, of course. And then here, what I would normally want to call the call stack, they're calling the backtrace. Exactly how did you get in this function that you're currently dealing with? Take a look at that. So you can see that at this point, right, the main function booted up, and then the main function sent us to this factorial function with a parameter of n being 5. And we are currently on line 31. Again, every time you call a function, you get another stack frame on the call stack to record the parameters and the local variables and the return address about where you need to go back. Okay, so I'm going to start hitting the next line here. Now, obviously, n is not 0, so that's false. We're going to jump down to line 34. You can see that's being kept track of right here. And so now I would like to do n times the factorial of n minus 1. But before I can do that, I need to go call the factorial function, which is the function I'm inside of right now, with the number 4. Okay, I'm going to hit into function. We're going to see that. So here's a new stack frame on the call stack. Now we've called the factorial function with the number 4. And we're back on line 31. Okay, well, n's not 0. That's false. So that's going to send us to line 34. All right, and you can see in order to get line 34 done, first of all, we have to call the factorial function. And what parameters are going to send in? Well, it's going to send in 3. Okay, so you get a new stack frame. We're starting to get a fairly deep call stack, which is very common in larger programs. So we just called factorial with an n of 3, and we're on line 31. Well, this if statement is false. That sends you to line 34, and now you have to call factorial again, this time with the number 2. Another stack frame right there, just called factorial with 2. This if statement is false, and you're back on line 34. You're going to call factorial with 1. There it is. This is false, and this calls it again. This time you're calling factorial with the number 0. All right, this is going to be different now. So you're on line 31 with n 0. Well, that's true. Therefore, it's going to send you to line 32, and you're going to return the number 1. Now, here's a little trick here. The way that this program has been compiled, the return value is being stored in the first register on the CPU. So keep an eye over here on EAX, and feel free to look at the decimal column because it's probably easier to see right now. That's where the return value is going to get stored on the CPU. So when I run line 32, you can see that 1 got put there. Right? That's where it's being temporarily stored. We're coming out of the factorial function at this point. So as you know, as the function wraps up, because we didn't have to do the else statement, right? That was the base case. You come out of this function here, you're going to pop the call stack, right? Pop that top thing off, look at what's left, and that's going to tell us where we need to go back to. Here it just happened. So it said, okay, you're going to have to go back to line 34, back when your n was 1. Okay, so now we've completed a factorial call, and the value of that is what's sitting over in EAX here, right? The return was 1. So as we do line 34 now, you're going to be doing the 1 from that return value times the 1 that the n is. Okay, and obviously 1 times 1 is 1. That's what you're going to return. Let's see that happen. Okay, so there's the 1 up in EAX, which happens to be the 1 times 1. Now that's not too exciting, but you're coming out of this version of the function, and you're going to see the call stack get popped, right? So that pops off. That sends us back to line 34 of this function back when n was 2. And now you have the return value of this call, which is the 1. So we're going to do 1 times what n currently is, which is 2. Now 2 times 1 is obviously 2, and you're going to see that show up over in EAX. You see that? Okay, there's the return value from that version of the function. You're wrapping up this function. You're going to pop the call stack. Okay, that sends you back to line 34, back when n was 3. Now the return value from this function call that we just did is 2. So we better do 2 times 3, and that's going to be 6. See, there's the 6 right there. Okay, so coming out of this version of the function, you pop the call stack. Now you're back on line 34, back when n was 4. Now you're getting a result of 6 from that function call right there, and n is currently 4. So now we're going to compute 4 times 6, which is 24, and we're going to return that over in EAX. See that? There's the 24 that you're getting as a result of this function call. Now you're coming out of the function, you wrap this up, you pop the call stack, you're back on line 34, back when n was 5, and this factorial call is giving you a 24. So we're going to be doing 5 times 24, and hey, 5 times 24, that's 120. That gets put in your return value over there, right? You're getting out of this function, and as usual, you're going to pop the call stack, look at what's left, and that's going to send us back to the main function at this point. Once that gets happy with that, and now you're back on line 20, right? That actually sent us back to line 20, and that did the job of printing out the 120 that was the return value from that. Right? That's totally how that works. And finally, if I get this back here, right? So obviously now you return 0 back to Windows, and there's the 0 right there. You wrap up this function, you pop this off the call stack, and now the program's actually over. Great. So, feel free to review that. Normally, we don't think about all those details, but the way that the recursive function call actually works is you wound up storing all those intermediate numbers on the call stack by virtue of the parameters. So there was this point where we had 5, 4, 3, 2, 1 all stored on the call stack in the parameters, and that's kind of the magic about where all those numbers got stored. But C++ just takes care of all those details for us, and as a high-level programmer, once we understand recursion, all we had to think about was call the function with one thing less, and it's going to take care of it for us. There's an illustration in the Gaddis book that kind of goes through the same thing, but I think it's useful to literally see it happening on the CPU on the call stack at least once. And that's the magic of recursion. Another example, Euclidean algorithm for greatest common divisors. This algorithm here has been known since Euclid, about over 2,000 years ago. It's a method to find the greatest common divisor of two integers. And it's something you need to do in all kinds of programs, particularly when you're working with fractions, right? You need to add fractions or subtract fractions or compare fractions or reduce fractions to the lowest common denominator, right? All these jobs you need to find greatest common divisors at some point for. A lot of other cases as well. So a fairly important algorithm. And here's what it is. It's probably about the fastest way to find GCDs actually, is you take the larger number and you divide it by the smaller number and you look at the remainder. Now, if there's no remainder, if the remainder is 0, you have your answer, it's the smaller number. So for example, if I'm dealing with 12 and 3, well, 12 divided by 3 has no remainder, the GCD is actually 3. Both 12 and 3 are divisible by 3, and that's the largest number that you can say that about, okay? Now, if you do have a remainder, right, if the remainder isn't 0, then you repeat that division with the smaller number that you started with and the remainder. And you just do it again. If that has a remainder, take that smaller number and that remainder and do the division again. At some point, your remainder will definitely become 0, and that's where the process stops. And whatever the smaller number is, that's the GCD of that pair, and the pair before it, and the pair before it, and the original two numbers, that's the same GCD of every single pair you ever did a division with. Maybe you've seen this before. So for example, what is the GCD of 140 and 98? Maybe pause the video and see if you can follow that process on paper, looking at remainders from divisions. And I'll give you a little hint. This only takes 3 steps. Here's the detail. Okay, so I'd start off and I do 140 divided by 98, right? We're doing integer division. We're not dealing with decimals here. So in that case, you get a quotient of 1 and a remainder of 42. We're not done yet. We're not done until you get a 0 remainder. So you take the smaller number 98 and you're going to divide it by the remainder you just got, which is 42. So 98 divided by 42 gives you a quotient of 2 and a remainder of 14. Still not done. We're going to take the smaller number 42, divide it by the remainder of 14. Here, that's happening here. Well, 42 divided by 14 does give you a quotient of 3 and a remainder of 0, and that indicates that you're done, right? We stop, and the answer is 14, the smaller number in that division that you just did. That's the GCD of this pair and the pair before it and the 140 and the 98, right? Feel free to double check that. 140 is obviously divisible by 14. 98 is also divisible by 14, and that's the greatest number that you can say that for. Great, totally works. And I'll also point out, obviously, you can't do this another step because another step will be 14 divided by 0, and you can't divide by 0. So obviously, you've got to stop before the point where you'd be dividing by 0. So that kind of makes sense. Now, I will say, right, you're kind of taking on faith that this always gives you the right answer. You're kind of owed a proof of that. That's the kind of thing that we would do in the discrete mathematics course. So when you do take your discrete math course, be on the lookout as we develop more tools for proving things in math and about computing algorithms. Be on the lookout for the point where we need to prove that the Euclidean algorithm always gives the right answer, and that's kind of what the discrete math course is for. Again, where I teach at CUNY Kingsborough, we call that discrete structures, which is CS 3500, but that's the point of that course, is to prove stuff like this. So we owe you that at some point in a future course. But let's think about implementing this. Assuming we agree that this always works, let's think about implementing this in C++. So I like the fact that the process is sort of repeating itself with smaller numbers. That's exactly the kind of thing that you need for a recursive function. And again, I'm going to focus on the recursive case first. So recursive case is that if I don't know the GCD of these two numbers, I can redo the division with the smaller number and the remainder that I got before, and the result of that is the same GCD. I think that's the essence of it. Let's take a look at that. So recursive case is if I want to know the GCD of x and y, I can compute the GCD with smaller numbers, right, with the y and the remainder of the division of x and y. Now, I'm writing this math style. When you get to the discrete math course, the remainder, we technically call that the modulus. And of course, in C++, we're going to write that with a percent sign. But in math writing, you just write mod for that same operation. So I'm writing this math style like you'll see in a discrete math course. But the important thing is the way that I wrote this on the right, it's involving smaller numbers. And that's what you need for a properly working recursive function, right? The y is the small of these two numbers. And the remainder, if I divide x by y, the remainder has to be smaller than y. Like if I divide a number by 5, right, the only options for the remainder are 0 through 4. Clearly something smaller than you're dividing by. So mathematically guaranteed that these two things are smaller than you started with, and the numbers are going down on each function call. Nice. Okay, now of course the base case is that if that division has a remainder of 0, if x mod of y is 0, then the smaller number actually is your answer. It actually is the y of those two things. So there's your base case. So again, feel free to pause the video, kind of meditate on what we're saying on this slide with our recursive design. Think through whether that makes sense based on what we're saying. Now again, we owe you a proof in the discrete math course that comes later on that this really does actually always work mathematically, but given that, think about whether that makes sense. And when you're ready, we'll see it on the next slide. Okay, so here it is in C++ code. Again, amazingly short. But the important thing is it's exactly what we were saying mathematically on the prior slide. Here is a function called GCD, and it takes two parameters, x and y. It's going to return an integer for the greatest common divisor. And as usual, here's your if-else with the base case. If x mod y gives you 0, if there's no remainder, return the smaller number. That's the GCD. In any other case, call this function GCD with these smaller numbers, with the y as your first parameter and x mod y, which again has got to be less than y mathematically. It's got to be with these smaller numbers, and there's your recursive call, and whatever the answer is to that is the answer to my larger problem. Nice. Okay, so again, incredibly short, right? Incredibly short to read, which is what we like. I think that's what Alan Perlis was talking about, of trading description for time. Of course, this really runs on a CPU, and it stores intermediate values on the call stack, and all that kind of work's going to happen automatically. If you have access to the book lecture code, feel free to boot this up and compile it and test it a couple times. Totally works. Really short, and that's what we like. Now, again, I would expect to see this as an example in my assembly language class, my computer architecture class probably. So once again, at our school, when you take CS 1400, if that's coming in the near future for you, again, if you're having trouble with your GCD function at the assembly language level, come back here and review it and think about how very short and very simple the main idea is, and maybe that can give you some guidance for what you're trying to do in the assembly language. Great example. Okay, so I think that's a pretty good introduction to recursion. And remember that when you're designing a recursive function, you need these two parts. You need the base case, you need the recursive case. I try to design the recursive case first because that's really the essential, interesting part of the problem. And what I do with my students next is I'd get together for this lab, and I'd actually look at this programming challenge in the book 19.5 that asks us to write a recursive multiplication function. Multiplication function takes two parameters, non-negative integers, and tries to get the product, right, if you multiply them, with a recursive function call. Here's some things you're not allowed to do here. And even if you don't have the book, you can totally do this on your own. Here's some things you're not allowed to do here. You're not allowed to use a for loop. You're not allowed to use a while loop or a do while loop. You are not allowed to use the star. You're not allowed to use the star multiplying operator. The only two things you're allowed to use here are the plus sign and a call to the function that you're inside. That's all you need. Now, as a little hint, remember, multiplying is really repeated addition. Okay, so think about that factorial example maybe, and think about if I had repeated additions that I needed to do, could I do one little piece of the addition and then ask this function that I'm in for the other additions that are one step less? That's more or less really what needs to happen here. But you're not allowed to use the star symbol here, just plus and the function that you're creating. And that's all you need. So that's a really good exercise. Again, expect to see a very short function, but it might take some time to think through how the recursion works. And then actually, if that works, like the next challenge is a recursive exponentiation function. Now for that, you could use star, but you can't use the POW function, right, for that. So think about that. Those are good exercises. Now, pretty good introduction to recursion. Admittedly, these were pretty simple examples we saw today. We saw the factorial function, we saw GCD. And look, admittedly, you can write functions, alternative functions that do use a for loop or a while loop to get those things done. And maybe in some sense, that would actually be easier or possibly even faster on the CPU for those simple initial examples. We're just using that to get into the recursive idea. So what we really want to see in the next video is we want to see some problem solving with recursion of slightly more interesting jobs where clearly it's easier to think about and easier to get accomplished with recursion, and jobs I would not want to use a for loop for, not want to use a while loop for. That's what's going to happen next time, and hopefully that sounds interesting, and I hope you'll join me for that. I'll see you then.